Hi everyone. If you like the way I teach and want me to be your teacher, the link to my engineering fundamental school is in the description below. Enjoy the video. Let's start off the video how we usually start off the video by stating Newton's second law with the static equilibrium assumption. We've already reviewed in the previous video units, and we also reviewed adding vectors. Some of you may be curious on why I mention this in each video that I do. My goal is to connect these ideas in your mind and demonstrate that there is a flow to how the new topics are going to be taught. So naturally, after we discuss the second law, your next question should be, what about the third law? So that's what we're going to review in this video. Newton's third law, it's the law of action and reaction. What it says is that every action has an equal and opposite reaction. Let's say we were observing the free body diagram of a single cable. Let's say this cable was under a tensile force of 10 pounds. And of course, if there is a tensile force of 10 pounds on the left, there must be, on the other side by Newton's second law, an equal and opposite force on the right, so that we reach static equilibrium. Now I have a question for you. What side does the tension in the cable point when we free the body at this section that I'm going to draw, section A? What you should reply to that question is that the free body diagram, the direction of that tension is going to be dependent on which side exactly we choose to look at. And sometimes it could be dependent on the location of this cut. But in this case, it's independent of the location. We can see that if we slide A to the left or to the right, the tension in the section will always be equal to 10 pounds. Let's explore the left side free body diagram and see how that's going to look. We'll draw what's to the left of the section with the 10-pound external force and the internal force, which has to be equal to 10 pounds. Note its orientation is up and to the right. What if we did the right-hand side free body diagram? Once we draw that external force of 10 pounds by equilibrium, we'll have an equal and opposite 10-pound down and to the left. Now note, it's dependent on which free body diagram you're looking at. On the left-hand side free body diagram, the tension is up and to the right. But on the right-hand side free body diagram, the tension is down and to the left. The tension is, of course, the same magnitude, right? If you're in a cable, the tension is going to be the same everywhere. But the direction of that tension is going to change dependent on which side you're looking at. Let's say we put these two free body diagrams back together, the left-hand side and the right-hand side. What we're going to get is that the 10 pounds is going to end up canceling at the interface where we cut. And we should end up back with exactly what we started with. You can see those 10 pounds are going to cancel in the center, and we end up back with the original diagram. No matter where we cut, the tension will always have the same magnitude. And of course, that's since we're looking at a single cable. That's an important idea. Let's explore our first example, drawing free body diagrams as an exercise. Let's say we had two boxes hung from two cables. These are the two cables hanging from the ceiling. One is at a 30-degree incline and the other one has a slope, 3 run and 4 rise. There's a box D and a box E with associated masses. The mass of box D is 100 pounds and the mass of box E is 200 pounds. The question that I'd like you to try on your own is find the tension in every cable. Please give this question a try. Okay, I hope you've attempted the question. Now let's go on and solve. And you can compare to your answer. How many unknowns are there in this problem? Well, we know that each cable only has one tension inside. The magnitude of the tensile force in a single cable is exactly the same no matter where we cut. It's only that direction is going to change. So all we really have to do is count the number of cables. We can see there's 4 cables in the problem, so there's 4 unknown tensions. Let's assess how many equations we have. We know that the sum of the forces must be equal to 0. This is a vector equation. We can break it down into its two scalar equations by projecting in the I and j directions. Looks like we have 2 equations, but we can repeatedly use Newton's second law with the static equilibrium assumption at different sections to get more and more equations. At section DE, we see we have 1 projection in the j direction. Same thing at section CD. What about at section C? If we make a circular cut at section C, we see we have 2 more unknowns, and we can project out those 2 unknowns into 2 equations. With 4 equations and 4 unknowns, we'd be able to solve. Let's copy this diagram. The first thing we're going to draw is the free body diagram of section DE. Now this free body diagram is pretty simple. It just has the weight as an external force and the internal tensile force, which is unknown, inside of the cable. But we can quickly see by inspection or by the sum of the forces in the y direction that that tension in the cable is going to be equal to the weight. Right here, we're just reviewing that conversion between pound mass and pound force. Remember that if the gravity is equal to 32.2, the magnitude, the mass, and the weight are going to be exactly the same. That's why you see no transformation between the mass unit and the weight unit. 200-pound mass is 200-pound force. So we know that tension in section D. Let's write that down. Let's move on to the next free body diagram, which is the free body of section CD. We have 2 boxes below, box E and box D. They each have associated weights. We gave the mass, which was a 100-pound mass, but we can see a 100-pound mass and a 100-pound force are going to be the same. And the bottom box is 200-pound force. We drew that unknown tension, tension CD, and now we're working to solve this one. It's clear that what we're going to have to do is do the sum of the forces in the y direction, and we'll get 100 plus 200 is going to be 300-pound force as the unknown tension in CD. Let's move on to the free body diagram of section C. Let's draw our 2 cables, and we section those cables cut along the section C. So let's draw those tensions. And we'll also illustrate the Newton's third law idea, which is equal and opposite. Right? You can see that bottom part of the free body diagram is hanging down. Equal and opposite, we drew tension CD. Let's put our other tensions in and begin to solve the problem. There's some initial geometry to work out, noting the angle and using the slope triangle. The slope triangle is useful because it'll let us read off the cosine and sine. Don't find the inverse tangent and then find that angle theta. We can read off what the sine and cosine is. Let's sum the forces and project it. Let's first project it in the y direction. If we look at the sum of the forces in the y direction by projecting in the j direction, that's the sine component plus tension AC, the cosine component, minus 300. We can move that minus 300 over and we can solve. That's our first equation shown here. Let's sum forces in the x direction. That's our second equation. We'll plug our second equation into our first equation to solve for tension in cable BC. Let's isolate the tension BC and get the answer, which is the tension in cable BC is equal to 163.11 pounds. We could plug that into our second equation shown above, and we'll get that the tension in cable AC is 195 pounds. Let's summarize the solution here by rewriting all the tensions in the cable. Here's our final answer. Let's move on to another example. Now again, I'd like you to solve this problem on your own after I finish writing down the problem statement. What we have here is an inclined plane with a block A. The block A is connected to a pulley, which is connected to block B with the same cable. There is a slope associated with this block. What we want to do is find the weight of box B such that we have equilibrium, assuming that the weight of block A is equal to 75 pounds and the friction coefficient is equal to 0. So we're neglecting friction. Please try to solve the problem. Okay. Now, some of the questions students ask at this point is, what free body diagram do we draw? If we draw the free body diagram of this section shown here, we'd find that tension, but we don't know the weight of box B. So after we draw this free body diagram, we can conclude that the tension is just equal to the weight of box B by summing forces in the y direction. Now let's draw the free body diagram of box A. The box is at some angle, and some of the forces on that box is the normal force, the weight, and the tension force in that cable, which we just realized is the weight of box B. If we shift our coordinate system to align I and J with the unknown tension, we will reduce our work. We only have to break the weight of box A into components. If we use a regular coordinate system where the x-axis is horizontal and the y-axis is vertical, we have to break the tension and the normal force into two components, which is more work. If we do Newton's second law, we know we have two equations and two unknowns. We can find that normal force and the tension, noting that that tension is the weight of box B that we're looking for. Now we don't want to do extra work, so we don't care about the normal force. All that we really care about is finding that tension, which can be found if we project the equation onto the x-axis. Let's work out some of the geometry here. We can see that that angle must be 90 minus theta, such that this angle is theta, so we can complete our equation. We know what the sine of theta is 12/13. We can plug in the weight of box A, which is 75 pounds, and we get the final answer shown here. I hope this video was a good practice of drawing free body diagrams and really understanding Newton's third law. I hope to see you in the next video. Keep learning and keep working hard. Goodbye.